Hi everybody, this video is for an explanation of Dalton's law of partial pressures. But before we do anything with pressure, we have to review what we talked about in the very first video, section 11.1, about gases and pressure. We need to make sure that everybody knows how to convert from one unit of gas, like 1 atmosphere, into millimeters of mercury, torr, or to kPa, kilopascals. All of these units are equal to one another, so especially important in Dalton's law that all of your pressure units are the same and you are adding and subtracting and multiplying and dividing by mmHg and kPa, torr, or atmospheres, and not a different unit. Okay, so that in mind, here is Dalton's law of partial pressure. This comes from, yes, the father of chemistry, John Dalton, in the 17th century. He did a lot of very rudimentary, well, now rudimentary, considered rudimentary experiments where he was weighing gases and different substances with a very specific scale, looking at pressure readings, volumes, and what he found is that if he looked at a mixed gas, so that'd be something like air, which is a mixture of lots of different kinds of gases, that it is a sum of the pressure of that mixed gas is a sum of the partial pressures of the parts of that gas. So we use the equation P total equals P1 plus P2 plus however many gases are in that mixture. So we just use the general term Pn. Okay, so going up to 5, 6, 7, however many gases that you would use. So how is Dalton's law of partial pressures used? Well, one, it can be used to figure out what the pressure is of the different gases in the air that we breathe. So this little graphic has, yes, we breathe mostly nitrogen when we breathe in our air. 78.04% of the air that we breathe is going to be nitrogen, 20% is going to be oxygen, 0.9% is going to be argon, and this little fraction here is going to be other gases, which then you can see is the carbon dioxide, neon gas, helium, methane, krypton, hydrogen, in all these insanely small fractionated amounts, and hopefully not a whole lot of pollution wherever it is that you are. But we can figure out what the partial pressure of all of these different substances are by looking at the total pressure and looking at the fractions. So another way that we can use Dalton's law is when we end up actually using and developing or producing a gas in laboratory experiments. Okay, so in a lab, if scientists are going to be making some sort of gas as a product and they want to collect it, it's always going to be tainted with the air that we breathe. Okay, so air is always going to be a problem. So scientists said we're going to collect gas over water because they can make sure that there is no air in one of these little beehive contraptions before they end up starting. So over here you'll see you have a boiling tube. Here's some sodium acetate and some soda lime. It's heated up with the Bunsen burner. Gas is produced. It's being forced out of this one-hole stopper. The delivery tube goes into a trough that's filled with water here. And then when the delivery tube bubbles, when this air pressure builds and collects in here, you'll see that the air is going to add up at the top and it's going to force the water level down. So you can then collect the methane gas and all of that right there. But as we learned in the states of matter chapter, that water vaporizes. So we have to subtract out how much of the gas we actually have that is due to the evaporation or vaporization of water. Okay, that trough setup is very big and kind of cumbersome, so sometimes we end up using A eudiometer, one of my favorite words in chemistry. A eudiometer is basically a huge test tube, okay? And that test tube is filled with water. In school, I actually take a little piece of magnesium ribbon right here, all right? And I tether it to a little piece of string and a one-hole stopper. So here is my magnesium. I fill up a eudiometer right side up. So here's the opening. Here's your eudiometer. I fill about 15 milliliters of hydrochloric acid. So we are doing the single replacement reaction, Mg plus HCl. The magnesium comes in, replaces the hydrogen, and we get MgCl2 and H2 gas produced, and we collect hydrogen. This obviously needs to be balanced, but we see that we have two HCl's in here. So we then fill this the rest of the way with water until we have a very little bit of water actually spill out, ensuring that there is no air in here whatsoever. Don't worry, the hydrochloric acid is more dense than the water, so it's going to stay at the bottom. And then we put the magnesium stopper right here. We put our finger over the hole at the top, and then we invert it upside down quickly underwater. The hydrochloric acid, which was at the bottom, is now at the top up here. This is going to trickle down because it is more dense. It actually has this really cool bubbly effect. When it hits the magnesium right here, it's going to rapidly produce the hydrogen gas. The hydrogen gas is going to float up to the top, all the way up here. So this is now hydrogen gas in here. It pushes the water level down through that opening, and voila, we end up getting a little bit more water in the container, and we can read exactly how many milliliters of hydrogen gas are produced in our eudiometer, because the eudiometer is graduated with milliliter increments, and you can use stoichiometry to figure out exactly how much you are supposed to make and do make. It's a great lab. It's totally awesome. But the problem with the lab is water evaporates. So in that test tube, in that eudiometer that we have, okay, so it's inverted. You have hydrogen gas and you have some water that is here. Some of this water has vaporized. So this is referred to as wet gas. Oh, I know, all the jokes, wet gas. But that means that there is some water vapor in here. So water vapor needs to be accounted for. So we use Dalton's law in order to figure out how much the pressure of the dry gas is going to be. So the total pressure, so you can figure out from the pressure of the room, you can use the water vapor pressure, and then you can subtract out the water vapor pressure from the total pressure in order to figure out what the dry gas is from the lab. Okay, all of the vapor pressures that we use come from a data table. They are all constants. Scientists have repeated this experiment over and over and over again, and you get this huge table that looks like this. All right, and what you end up seeing is whatever the temperature is of the room that you are doing the experiment in, you can figure out what the vapor pressure of the water is. And it should be no surprise that at a colder temperature, like 20 degrees Celsius, the vapor pressure is 17.53 torr. So again, make sure that you have the right units in there. And then I've done this experiment in the end of spring when the temperature was actually like 24 degrees Celsius in my room, and the vapor pressure was 22.3. And there's a big difference from doing this like with a period 1 class versus the period 8 class, because it warms up as you go through the day and you have to subtract the larger vapor pressure. So very important table to look at. Okay, and that should be provided to you in the problem. So Dalton's law of partial pressure sample problem might give you some information that you might not actually need. Okay, so be careful with that. A 250 milliliter sample of oxygen gas is collected over water at 21 degrees Celsius and has a pressure of 780 torr. The vapor pressure of water at 21 degrees Celsius is 18.7 torr. What is the pressure of the dry gas alone? So some pro tips to consider. If you see dry gas, if you see collected over water, this is a Dalton's law of partial pressure problem. It gives you two temperatures, but it's the same temperature, and that temperature is not actually used directly in the problem. That temperature is just used in order to figure out what the pressure constant would be, or the vapor pressure constant would be for the water. So this sample, this volume, is not actually used either. It's just giving you that there is a sample that is used. The information that you actually need to solve this problem is the total pressure, okay? You need to note the vapor pressure of the water and that you are looking for the dry gas alone. So we have P total equal to 780 torr. We know that the pressure of the water at 21 degrees Celsius, which is why we needed the temperature, is 18.7 torr, and we want to know the pressure of the dry oxygen gas. So I'm going to plug this into P total equals pressure of the vapor pressure of the water plus the pressure of the dry O2. And we see 780 torr is equal to 18.7 torr. Yes, have to make sure your units are the same. And the dry O2 is over here. So how do I solve this? Be careful. This is an addition sign. So all I have to do is subtract 18.7 torr from both sides. It's the simplest of all of the gas law problems. So the pressure of the dry oxygen gas is, grab your calculators, push pause if you need some time to go grab it, is 780 minus 18.7, and we get 761.3 torr. That's the pressure of your dry gas. Okay, that's without the vapor pressure of the water. So here you can see how it's all done out in the notes. And you got your 761.3 torr. And that is Dalton's law of partial pressure.